Just start filling in one. So, oh, okay, any questions on the sample size? We went over that last time. We just solved that equation. Yeah. Right, or you could go conservative if you want to. All that means is you put 1/2 in there for P and Q. And then if you want, you could square root of 1/4. So you can just write it like this. That would be the conservative solution. It's a pretty big difference if P is close to 0 or P is close to 1. So if you have some prior knowledge, at least of that, you should use it. Sampling is expensive, and you want to draw a good sample. The larger the sample size becomes, probably the harder it is to control. You might have a survey, and you say, well, I'll have 200, I'll give one person do 100 of them, and the other person do the other 100. But if you don't train them well, if you give them different surveys, you just have 2 samples of size on that. So, it pays to try to determine the sample size. If you have some prior information. Okay, so let's look at, and that's just plug and chug. Right? I mean, you might have to use a prior estimate P, that's a problem 1013. We refer back to 110. Portion cured is 25 over 80. So, 31%. So if you use that, then within 10%, so E is 0.9. Gas, just use that one. Just call it 0.30. You want 95% confidence. So then it's just plug and chug. Oh, you're done to hand calculator. Any questions on that? If you go the conservative route, then you'll have 1/2 instead of this 0.21. No, you have 1/4. Okay, 13, we have a test situation, H plus P is 0.7. Right? And the alternative is P greater than 0.7. S is the number of successes. Now, in this problem, we can just use S. We don't have to do the Z. I think we did the Z last time. That's what we'll be doing. We'll go back and forth on it. So why don't we just stick with this notation? In this case, this problem is determine K if alpha is 10 and n is 80.
Can I ask a question? If S stands for the number of successes, what would you say K stands for? What do you call that?
K you have to determine. Okay?
So it's just to point out to
And that's,
the right of S.
why don't we set up a test and then let's just do it like we would in practice. Okay, we're going to go through the exercise. So what if you wanted to set up, like on part, we'll do part A for sure. We're going to set the test up so alpha is about 10%. Okay? And then that means you have to determine K. So we want this to be true. This will be about 10%, the probability under H0 that S is greater than equal to K. Okay? Now, what's under H0 mean here? That means P is 0.7, and S is binomial, right? We know N is 80, that's given to us. This is all given. P is 0.7, so that's what we want to determine. So you would have to solve it like that, that's right. Then you could use the tables. You could use the tables, or you could just use your favorite package. Or we could span it as templates. We'll just solve it. We need a table, right? And I can give you a table. Let me set the table up so okay, so it's going to be about what? Well, we'd expect, we'd have to know where to look in a table. Okay. We'd expect S to be what? 80 times 0.7, which would be about 56. So it's no use looking until we hit about 60 or so. Well, in fact, we'll do the range from 56. Well, we'll go with this. Okay, so here we go. And we want, what, 10%, so we're between 61 and 62. So K is, if K is 62, then the level will be 0.087. Okay, so we got that from the table. That's what you would have to do. I have the Z for the test problem. We'll do it with a Z formulation. But that would be the level of the test. K would be, if you take K to be 62. So in this problem, if you're testing P equal 0.7, right? So the binomial would be like this. It would peak at 56, right? That would be the null mean. And if you go out here to 62, then the probability from that point on is about 80%. So then our test would be, you reject H naught if S is greater than or equal to 62, and the probability of type 1 error is about 80%. Okay, so that would be setting up the test. Okay, and then, okay, let's do it like we would in practice. So in practice, we would have this, right? In practice, you would know your hypotheses. You have to know your hypotheses. And this is a one-sided test. Okay, and then you would just look at the data. Right? And then you would determine from data how big K is and what the observed significance is. Okay, so then suppose you look at the data, and I'll generate some data. What? N is 80. Let's do an alternative situation and see if we reject. So let's say P is, we don't know it, but it's 0.75. So okay, so there's our data, right? I generated it. This is on the left side of the wall. This is on the right side. This is where we are in practice. Okay. So we count the number of successes. So it's what? 4, 8, 12, 15, whatever that, 17, 19, 20, 22, 24, 26, 28, 29, 31, 37, 4, 5, 6, 7, 58, 59, 60, 61, okay? So if we were doing our test, we couldn't reject. So we observe S is 61, so if we're doing this 10% test we just put together, we would fail or reject, right? So in part A, you fail or reject. Not big enough. It's got to get to 62 in part A. Here you're at 61. And all means 56. But in practice, what you do, you wouldn't be doing that problem. You would be using observed samples. And so then you're going to compute the probability that binomial, right, with n equal to 80 and p equal to 0.7 is greater than or equal to 61. That would be your observed samples. Okay. Then let's do it for the exam. For the exam, you won't have binomial tables, so we'll just make a z-critical point out of it and approximate the probability that way. So we just want to standardize this, and then you might use the continuity correction. You want to include 61, so I would suggest backing up to 60.5, right? And then you need to know the mean, but the mean is just n times p, right? Just said 6. And you need to know the variance, which is npq. So 16.8. Actually, I need a standard deviation. So that I would have to calculate with my calculator. That's 4.10. And now I'm set. I can just make that a z-critical point. Right? Z would be 60.5 on this 56. And then I have to go back to my calculator. 4.5 divided by 4.5. So that's 1.1. So it's a probability that standard normal is greater than 15. I make that mistake. That seems like it's not big enough. Because we almost rejected at the 8%. Then you could get this. Oh no, never mind. That's 13%. You get definitely wrong too. This is what you get in that. Okay? That's how I want you to do it. So that's how you would do it in practice. Any questions on that? So on Thursday, if you can, that's what I want you to do for a test like this. I'm not going to give you my number table. I'll give you the numbers. So you just define the users. Now this is the lowest level at which you could reject H0. So the lowest alpha level of rejection is 0.1357. So if you're a government person, then at the 5% level, you cannot reject H0. So that's always good part of the quiz too. Actually, the question would be phrased, conclude in terms of alpha equals to 5% or alpha equals to alpha. Because I want you to make a conclusion. You fail to reject H0. There's insufficient evidence. To conclude that P is greater than this. Right? You might say. And then in practice, that often means that you just retain H0. Retaining H0 brings in the probability of type 2, but that's what happens usually in practice. So, go ahead and knock over H0, and you didn't knock it. Any questions on that? Okay, so let's look at the power of the test. The power of the test is a probability you can't knock it over. And this is, if I put up that table, under the probability of type 2, this is probably separate. And it's so this is 1 minus the probability that you reject. And this thing is the power of the test. Last depends on H sub A. So let's go back to our test that we set up so much difficulty, okay? Our great 8% test. So let's go back to how far goes. Test is rejected. That's where it is. And again, H0 is P is equal to 0.7, and the alternative is P is greater than this. So the power of the test is the probability under HA. Well, under HA, P is just greater than 0.7. I don't know what value to stick into the binomial. So it actually becomes a function of p, right? So really the power of the test is a curve. We like to use Greek letters so everyone gets confused. Okay, we usually call ham of p. So it's probably p that's greater than 62. See, it's just this. We know n is 80. It stays the same. Then what you want to do is you want to plot that for various values of p. When p is equal to point, we got one thing on it already. When p is 0.70, we know this is 0.0873. So if it's just a curve, we usually have a graph here. We locate this, and this value is your alpha. And then what you want to do is put in some more values and make a curve. If you think about it, it's going to get high. It's a probability if you don't get to 1, there's a bit. It's going to get high, right? And as p grows. Okay. So we just have to go, we could do 1. How about like p equal 0.8? Let's do 1. How about 0.7? And we can calculate that. See, that comes out to, I don't like to keep going back, but I wish I had 2 screens. Yeah, that's what you'd have to look up in the table, right? It would be the complement. N's 80 and P's 0.75. And it's 30, it's about 35%. So that means your test has a 35% chance of detecting P equal 0.75. And that's really what you're usually interested in, okay? Usually the alternative is your baby, it's your thesis, or whatever. It's a thing of interest. And you do want to reject H0. Well, if P is 0.75, you should reject H0. But you'll only reject it with probability 35%. Not that high. 3 out of 10. Most of the time you're going to miss it. You don't have that much power at 75. So then what do you do? What if you wanted a lot of power at 75? What's just the intuitive answer? What if you want this?
Increase your sample.
Yeah, just increase the sample size, right? You'll drive that up. And of course, then we test it how critical changes too. You will. Well, then, suppose you're lazy like me. Just put in some peace. Let's do P's that go under 0.7. So let's go like at 0.6. Let's go up the steps. So let's look at a lot of P's at once. this stays the same, okay? It's a test, okay, I'm looking at the power at 61, it's a complement, n stays the same. So what p's. There's 0.7, right? It's our level. So these are all the powers, and they increase as p increases. And they decrease on the other side. So, you know, Foxworth's 1,000 volts. So we just plot p's. So there's our power. 0.7, that's our level, right? And then it's under this. Okay. It stays under alpha to the left. Of course, it's above alpha to the right. Thank goodness, right? You want to, well, on one-sided test on this side, you want an increase in power. It would be horrible to have a test that goes up and comes down. I've seen them. It's the rank transfer. That's what will happen to him. You always want a monotone power. Okay. If you want to detect 0.8, 0.9, things like that, you've got a very good chance of detecting it. Now, suppose you're a government person, and the government person, laser pointer. The government person will draw a line at 0.8. We'll say you have to design your study so you have any chance of detecting a certain value. And in this case, it would be what? It almost be, that's just a coincidence. Probably above it, right? I can do it with the mouse. So I can get it out here. Yeah, it's above it. It's about right here. So you might have designed your study to do that. You know, that's, it's like you draw a line in the sand. I've got to be able to check this. This is a practical interest. You know, it might be like a new cure rate or something, maybe some drug. The standard treatment gives you a cure of 60% of the time. If your new drug's 61%, 62%, but boy, if it's around 65%, that's an improvement, or 70%. That's that value. You might design your test so you have power about 80%. Okay. The other thing we should talk about is I guess we should go to another thing. Suppose we decrease alpha. Suppose we're going back to the problem. Suppose you want a 5% test. You want a 5% test. I need that. Okay. Suppose you want a 5% test, and then you should take K to be what, 63, right? 63 gives you a 5% test in this case. Okay, now so we have test one. Test 2. That's 63. .5%. And what's going to happen to your par in that case? What's going to happen to the par? Your first level is pretty high, 50%.
Increase your power when you decrease.
Right,
the
you'll
alpha.
decrease the power, right? The test has to work harder, it has to get up to 63 to reject. Okay.
In our practical application, you would never reject it. This test came in at 61. You can see that, you can just draw it, top of the other. This would be 62, and it's the comp. So you're going to adjust the bold line would be 5%. So you just have more power, okay? But that much more power at 7.75. So that's true in general. Algorithm. So hence the probability of type 2 goes up. Type 1 and type 2 are seesaw. Okay. I push down type 1, then type 2 goes up. The statistician thinks in terms of power, not in terms of type 2. Sometimes engineers think in terms of power and type 2. Okay, the last thing let's look at is, we're spending a lot of time on this, but let's look at a two-sided test. And let's look at like 50%. This is pure scientist. Now, when you reject H naught in favor of HA, you reject if S is too small or S is too large. Right? It's a two-sided test, and that not equal is abbreviation for this, and at times you might want to even write this down. So when we reject if S is too small, right? Or if S is too large. Now n over 2 is the expected value in this case, because p is 1/2 under h naught, right? So you know k is down here, and you know L is up here. It's always nice to scratch down a number line and put your symbols there. So then you have to find two values. Okay. And usually you cut your alpha in half. In this case, it's symmetrical. That's exactly what you would do. Okay, so you'd have to find k this way. And p is 1. Okay, so you can find more than that. Let's just do a practical one. Let's do a practical problem. Suppose we are testing this, and let's use a different n. Suppose n is 40. So the data comes in. We had 40 observations, and we had okay, so let's do the observed significance one. See if we can reject, say, 5%. Well, what's your significance one? You're on the downside, right? You'd expect 20 and you observe 16. Okay. So it's like S less than or equal to this one, right? So this would be, at first you would think this is your p-value. Are you small enough? Right? But it's you start with a two-sided test, you can't change in between. And you pay a price for your ignorance. The two-sided alternative is like I call it the alternative ignorance every once in a while, because you don't know anything. And if you don't know anything, you have to pay the price at the end, and the price is you just double that p-value. So the observed significance, I don't know what it is. Price. Two-sided test. Okay. Any questions on that? See if we compute this. We could do a normal approximation, then we just do it fast. And just do 16. P is 1. It's pretty high anyway. So that would be the p-value. See, after the fact, you say, oh, yeah, guess what? It was one-sided anyways. But no, you have to double that. You have 26% as your p-value. So you're not going to reject H naught. Even at 13%, it's too high. That's the price you have to pay. So it becomes double. Okay, this came up in an important investigation, well, this about 15 years ago. So by that time, we understood that the smoking causes lung cancer. That's what the cigarette industry knew in the 50s. They had the data, initially saying something about it. They just didn't do it. Everyone just kept on smoking. And then finally, the evidence just became too solid. Okay. So it was established that smoking causes lung cancer. So then they started thinking about secondhand smoke. And the government set up these investigations for secondhand smoke. And we already knew it caused lung cancer. So the government was not ignorant. So they did one-sided test. And the tobacco industry fought for a two-sided test. Right. Because the government could show it maybe at 0.03, and the cigarette industry wanted them to double that, so it's 0.06. So it's not significant. So they fought. They still fight. I don't understand. The government one they just used a one-sided test that showed secondhand smoke also was linked to lung cancer. And finally, you can go bowling again. I know if you're a smoker. You know, many years ago, my wife and I went bowling. We hadn't bowled for years, and it was so smoky. We had to come home and wash it, just take a shower and everything else. And we said we won't go bowling again. Now you can actually go bowling because it's that's my introduction to sewage. So that comes up every once in a while. Okay, so finally we're done with let's talk a little bit about the unsampled discrete problem. I think the discrete problems are part of this course. So there's discrete problems and continuous problems, and I'll just try to do that as, so there's only a few things to add on, and then we can go on to continuous. In the discrete case, the random variable of interest just has a finite range, and sometimes you make it have a finite range, okay? You take your continuous data and chop it up into categories. Don't do that unless you have to, right? You're going to lose power. I see people just do that without thinking. Just spin it up. No, don't spin it up. So we have random variable x of interest, right? This would be the probability model or behind the wall. It's discrete. So it either has a finite range or you can list it, right? These p's all have to add up to 1. Okay. Then, what are some things of interest on inference? You could try to estimate one of those p's, right? It's binomial, all right? Let's just pick on p1. You want to estimate p1. Everything else is failure. So we could do an estimate, a test, a confidence interval. That's all, we know all that. And then what else would be of interest? You might want to compare two p's, okay? Suppose this is during an election, and you've taken a poll of the candidates, and you have Obama and Mitt, let's say, a few months ago, and then everyone else. Then you'll want to look at the proportion for Obama minus the proportion for normal. So you want to estimate P1 minus P2, you want a confidence interval for it, and you might want to test a hypothesis. Okay? That's new, and we'll do that in a few minutes. All right? And then what else is new? You might want to test the whole distribution. Okay? You might have an idea, you might have a specific distribution in mind, where you specify all the P's, or you might have form in mind, like it's binomial, it's Poisson, and we'll do that. That's so to do these things, we need data. So we just go back, we observe the data. These are the only values. So there's only one distribution of the data. Then we observe. Those are a sample, right, on X. But these X's can only be 1 through K. And actually, they don't have to be numbers, right? It could be like hair color. But one's going to be no blonde, 2 brunette, so white car or whatever. Type of car, okay. GM, Ford, Toyota, etc. So then we observe this type of car, the next one is a Toyota, maybe the next guy bought a Ford, the next guy bought a Honda, etc. Then we observe those X's, but you suddenly don't list them. Suppose you did that, so you took a sample of size 1,000, and so you'd have 1,000 choices of cars, and then you give your boss that big sheet of paper. So, you know, you just put it in the distribution. You tally up the GMs, you tally up the Fords, so maybe you categorize it. So those J, X is equal to J, right? So this is the sample distribution. There's no other, right? You might merge categories, you have to be open. But for the moment, this we could have the generic. These are rows, right? Observed. Those are the observed frequencies. Those become the statistics of interest. How about old stuff? It's just this one. It's just those over. Those have to have. Right? And then this would be your confidence. Now I won't use Q here, so that's good. And again, you could do a test. Just do a test. Okay, that would be the usual test, it's often called the scores test. There's another test you could put in the estimate down there. But, that's the usual test. For statistics. Any question on that? That's what we just did, right? That's done, right? You say, well, maybe I can go through the whole table like this, but then you get a little bit scared because you're doing a lot of testing and you have, I won't talk about it today, but you have a multiple comparison problem when you start doing things like that, right? So we'll come back to that. Probably not Thursday. Okay. Any questions on that? Because that's what we just did, right? Now, definitely another one of interest is differences, okay? Just like that candidates poll, you have two front runners, you forget about everyone else. Well, actually, at the beginning of the primaries, that's not quite true. You'd be looking at more differences. But after a while, you just start settling on the two. So we'll spend the rest of it today on that. And it doesn't matter what two we pick, how about P1 and P2? So then we want to consider P1 minus P2. Certainly our estimate. The estimate should not surprise anyone here. What else would you use? So you do that in first grade. And then we have a standard error, and this is finally being put into elementary stat books. I couldn't believe it for years. They wouldn't talk about this, and then I'll be teaching the course in the fall, and the election will be on, and I definitely want to talk about that in class. Why not? Some of you may have not seen this. Okay. I don't know if you've seen that or not, but it's coming into the elementary stat books. The one I use in 364 is a problem. Something that should be measured, a major piece of inference, is relegated to the problems. So pass without okay. So this is our confidence intervals. It's a symmetric one. We just go through the asymptotics. And then you could do a test with it too. And that's what I want to talk about next. Any questions on that? Okay, Democrat, Republican, Libertarian, and something else. Actually, I should have independent. And it'd be more independent. So it's not very good call. Maybe we want to look at the difference between the probability of being a Democrat and the probability of being a Republican. So, the rest of it is straightforward. We read this again. So, crossing. Oh, it is. Yeah, right, it's a good test. So my estimate will be 4 minus 425, right? And I didn't do the standard error, it would be, that would be the standard error. So there's an example. Okay. Now, let's look at a test for this. The test would be, well, there's various hypotheses you can test. Often one of interest though. Oh, well, okay, before I finish that, I should have figured that standard error out. It might be in the book. Certainly, it's bigger than 0.015, okay? So this standard error, I don't know, it might be around 10%. Let me just say about 11%, so you can see where that comes from. So I do a bad calculation. So 2/3%. So there's my confidence. So there's my point estimate. Here's my error and the confidence. And again, that's a bad calculation. Now, that includes 0. This is a confidence interval where you're looking for 0 quite often, okay? And 0 is in this confidence interval, so it's inconclusive. You can't say anything about this poll as whether Democrats are more popular than Republicans. Because the confidence interval includes 0. If the confidence interval was like this, 0. If the confidence interval was like this, and I looked at Dems over Republicans, then the Dems have it. And if the confidence interval was like this, then the Republicans have it. When I have a confidence interval like this, and then on this side of the confidence interval, the Republicans have it. On this side of the confidence interval, the Democrats have it. So my confidence interval is inconclusive. It's inconclusive. 0 is in. You can't say anything. If you watch the media on TV quite often, they're trying to say a lot, but they shouldn't say anything. It's a toss-up. You have to say it's a toss-up, but. Now, suppose you just wanted to test P1 is equal to P2 versus, and this do a two-sided test. Now, you can do it by the confidence interval we just talked about, right? Or you can actually perform a test and you get a nice test statistic out of this. It's called McNemar's test, and it's used quite a bit. Sometimes it's overused. Okay, so you look at the Z-test for this, right? It's going to be, and now I want to go back to the others. It's O1 over N minus O2. And down the stairs, we have here, right? So that would be the correct thing. That would be the standard deviation. P hat 1 minus P hat 2. But H naught is true, okay? I'm gonna form my test statistic under H naught, all right? And then I'm gonna compare it with a large value. It's too large or too small. So I'm always formulating things under H naught. Well, if H naught is true, then P1 is equal to P2. And I don't have this in here. Right? This is the scores form of the test. You allowed me to do it, yes. A couple minutes ago, no one said anything. Now you're just stuck with it, right? Yes. That. One. With H naught. This is called the scores. So that piece goes by, right? And then I don't know P1 and P2, so I just put in O1 over plus O2. Now that'll be a z-test. Okay, we'll compare it with z critical values. And if you know a little bit about statistics, if you square a z, you get a chi-squared. And it's worth looking at here. So you look at chi-squared, which is just z squared in this case. And that would be, you get 1 squared. Honestly.
I think you're missing n square. On the denominator. It's supposed to be n square, right?
No, if I just square that, right?
The denominator.
Oh, right, that's right. Don't do, okay, you try to stop me. I wouldn't listen to you. There's a chance. That's not true. Speak up, please. So you want to so it's O1 minus O2 squared. O1 plus O2. This is called McNemar's test. Okay, under H0, this chi-squared is chi-squared 1. Has a chi-squared 1. Okay. Oh, it's time to quit. But we arrived it. I've done that before too. I forgot to divide by 1. So 1 over. Let's keep that 1. I get a double n. Then the n's cancel out. This is a neat test that we'll come back and on Thursday, we'll begin with this and we'll go through that example with maximized. And then, this test is really nice for significant change. I discussed that in the book. Actually, I just used it, I tried to study. So we'll begin there. And then on Thursday, there'll be a quiz at the end of class, right? And we'll go over everything from the last quiz. So we'll definitely go over estimates, the contents and the rules, the portions, right? And testing. And again, the observed significance level is what I'll be after. We'll have normal tables, so you could just set up a z-test. With the p-value. So again, you can have a cheat sheet, front and back, 8.5 by 11. Note, let's not have any laptops, please.